Welcome to this new Physics Matter colloquium, prepared for the Forum on International Physics, the FIP, at the American Physical Society, in the framework of the Physics for Development program. Those live online colloquia, primarily target and involve some test center selected from within the partner countries of the SESAMI project, which is the synchrotron light for experimental science and application in the Middle East. And this is a project supported by the APS. I will first introduce the member of our panel, Andrea Lossi, the scientific director of the SESAMI Light Source in Jordan. You will find as well some early colloquium with a very comprehensive description of the SESAMI capacity that he gave earlier. For the FIP panel, my name is Christine Dodd. I work at the European Spallation Source in Sweden, and I'm the vice chair of the FIP. We have organized this series with members of the FIP executive committee, share line, including Wisasi Farelli from Bologna University, Alan Hurd, our current FIP chair from Los Alamos, and Joe Nimela from the ICTP in Trieste. Engaging in science and physics as a vector for development. That's our goal. This series has been has started in the middle of the pandemic. With the purpose to reach and to engage developing community with inspiring topic in the field of physics. We want to promote international collaboration and tackle the quest for physics curiosity. The website that we have, you can find there more insight and topics showing why physics matters by renowned scientists and by Nobel laureates as well. As a matter of fact, the inauguration event by Wisasi Farelli and Paola Catapano presented last year the Polar Quest expedition, and last week, the second voyage successfully completed a 20-day scientific expedition in the Arctic archipelago. We will find more on our website about this interesting aspect. Science as a vector to transcend most boundary, gender, religion, and politics. Physics and science must promote a peaceful world. It's the responsibility of scientists. Those or each of the continents currently develop a coherent strategy for physics by bringing and giving birth to new research infrastructure, like mentioned last month. With the new African strategy for fundamental and applied physics and the future African light source. But as a symbol of international collaboration, the FIP, the Forum of International Physics, has chosen the SESAMI Light Source in the Middle East, which Center of Excellence has been built by scientists and for scientists, driven by those values. SESAMI has 8 members countries and 18 observer countries. We have already conducted scientific expedition in members country. In Jordan, for instance, with SESAMI, with a presentation by Andrea Lossi and Giram Kamel. In Pakistan, with Professor Hafez Orani, who hosted a presentation by Rod Lind from Los Alamos, describing the field dynamics of wildfire. We went as well to Israel, where Professor Alan Gross enchanted us with the music of physics. And in the next month, on September 30, we will travel to Iran to listen to the president of the Physical Society, Reza Echari, and we will be educated on the quantum information. Thanks to Professor Vahid Karimpour. Later on, we will learn more about science in Palestine, in Egypt, and other SESAMI member countries. But today, as an intermission, we would like to involve an observer country. And we have selected Brazil. We have selected the Sirius light source, and Dr. Harry Westfahl, will be our guest presenter. Dr. Harry Westfahl Jr., he's the director of the Brazilian Synchrotron Light Laboratories, the LNLS, since 2020. He also served the LNLS as a scientific director from 2013 to 2019, after several years as deputy scientific director, and has been a researcher there since 2001. So when he joined the laboratory after 3 years of postdoctoral research. So since 2013, so he coordinated the project on construction of the beamline for the new Brazilian light source, so the Sirius. And its main interest is on the physics of condensed matter system in the use of synchrotron radiation and for the studies of material, mainly the polymer, the magnetic material, and in the development of synchrotron radiation instrumentation. So he graduated with his bachelor and PhD in physics in the State University of Company, so in 1998. In Brazil, but he did as well his postdoctoral study in the University of Illinois in Urbana-Champaign. So since 1999 and up to 2001. So after this brief description, so I will leave the floor to Harris, and I will just comment that if you have questions, so you can raise your hand, and we will, if possible, so maybe prefer, or that depends on the flow as well. We like interaction, so that's also, if possible, during the presentation to raise your question, but we would really recommend to have a section at the end of the presentation with the question and answer. So now without further ado, so I leave the scene to Professor Harry Westfahl for his presentation.
Thank you, Christine. Thank you very much for the very kind introduction, especially thanks for the opportunity to be here with you and to tell a story about this new light source. Are you seeing? It doesn't look like I have the.
Yeah, maybe it's the other one, the other screen. This is your agenda.
Okay. How about that?
Yes, now that works.
You're seeing my presentation or my slide view?
Both. So maybe if you can
switch.
Voilà.
So, how about that?
Perfect. Perfect.
Now it's working?
Now it works very well. You can go ahead.
Perfect. So thank you very much. It's very exciting to be talking about this international endeavor, of course, that is to work in a synchrotron light source. So I will explain some of the current activities of the commissioning and the first scientific results that we see on the new light source, Brazilian light source. First, let me explain what we are inside the International Center. Let me change my. Okay. We are in the International Center for Research in Energy and Materials in Campinas. And we are a non-profit organization, private non-profit organization that works under contract with the Brazilian Ministry for Science, Technology and Innovation. So all this campus is funded by the Ministry of Science, Technology and Innovation. And it all started with the first Brazilian synchrotron light source. We call it UVX, is now currently decommissioned and being disassembled. This was a machine built entirely in Brazil that created the technology and know-how and even built the community, synchrotron community here in Brazil and Latin America for the new users, thousands of users that now are anxiously waiting to populate the beamlines and do their experiments. So this is LNLS, is the first initial lab that gave birth to this center, that now has more different labs with a variety of activities. LN Bio is a biology lab, has a leading facility for structural molecular biology, drug development, and cancer and cardiovascular biology. And I'll give you some examples of their research in cardiovascular biology research that's been using Sirius. LN Nano is the most comprehensive lab in nanoscience and nanotechnology in the country and possibly in Latin America. It has several different electron microscope, cryo-electron microscopy, nanofabrication facilities, also open for the international community of users. And LNBR is a laboratory that develops microbial platforms, which is kind of a facility as well, because they develop microbes for different production of different biorenewables in the semi-industrial scale. So they have all the infrastructure to of pilot plant from developing a microorganism to test ideas in a pilot plant scale as a facility. And they use the synchrotron as well as the other labs to investigate biomass and the biology of microorganisms in their transformation. So I'm gonna give some examples of what they are doing with the synchrotron. But first, let me show some aspect of our international collaborations and user base. So basically, you can see that we are here in Campinas, in the southeast of Brazil, and we have connections with most places in the world. This is a snapshot of 2019 collaboration user base of the center, CNPEM. And this is obviously for the synchrotron. Now we are still under commissioning, so we are mostly bringing users as what we call friendly users. But the intention is to grow the user base, especially the international user base, as this is one of the few synchrotrons in the world that is a fourth generation, and I will explain later why this is so exciting. This is our connections of the user base in Brazil, so it's a national lab, so basically we have groups working from different parts of the country in our facility in the different labs. Now, this is the outline of my talk. I'm going first give you a brief introduction of what is the evolution of the Sirius project from 2015, roughly 2021. Then I'll give you some general ideas of what we call the 4G storage ring and some of the scientific programs that we have been developing on the beamlines and quantum matter, living matter, and soils and functional matter. And then I'm going to give you some ideas of what we intend to do for user support and some of the R&D developments with local industries. So first of all, the Sirius project as it's currently developed, it was the current design, it was fruit from one of the international committees that oversees the project and evaluates the machine project. And by 2012, this machine was a third generation machine that was being designed. But we had at that point Max 4 leading the way for multi-bend achromats and fourth generation machines. So, and some of the members of this machine advisory committee back in 2012 provoked our scientists and engineers that we should design a fourth generation machine based on multi-bend achromats. This is a snapshot of the world of development of multi-bend achromats in 2013, when we just had decided to take this challenge and build Sirius as a fourth generation machine, while at that point there was no machine working as a fourth generation. There was Max 4 was being built and leading the way, but that was very ambitious to do that. And we were following behind with also with the other upgrades that were being planned with this new technology. So this was then back in 2015, January 2015 was the groundbreaking for this project. It was a greenfield facility. So you can see some of the timeline of construction, the civil construction. And in October 2019, we had this building almost ready. Of course, accelerator and beamline development were following in parallel with different teams. And this was the result that we had, and we now have this machine operating in commissioning mode. So this is an overview. For those who are not so familiar with synchrotron, let me give you a quick view. So you see this big stadium and infrastructure, and what you see inside is accelerators. So you have a linear accelerator, and two synchrotron accelerators, and the one that we extract light is what we call storage ring. And what we do is we store electrons in this at the speed of light, and they circulate in this machine, as you see in this animation, at the speed of light in bunches that have a specific size, dimensions that I'm going to mention, and this provides us the radiation in the ample spectrum that depends a lot on how these electrons are shaped. The electron beams are shaped. So, and we use this radiation in what we call this beamlines, the experimental stations that direct the light that comes out tangentially from this storage ring. So the electrons that circulate in the storage ring, these are divided in bunches, and this structure is dependent on the project. But in our case, this bunch is of order of magnitude of 10 microns only. It's a bunch of electrons with a few microns only of thickness in the vertical direction. and a length of a few millimeters, or picoseconds if you translate from this package moving in the speed of light. They typically carry billions of electrons per package for the typical currents of 100 milliampere. This is not in scale, of course, but what we have is essentially continuous light source, right? The packages are separated by 2 nanoseconds, so it's for all purposes. We are basically have continuous synchrotron radiation coming to the experiments. And let me show you some of the components of the system. This is the LINAC. The LINAC was actually produced again by an international collaboration with Shanghai Synchrotron. So this was built and delivered to this new synchrotron. And then we had the booster and the storage ring all built, and it's a 3GeV booster, so it's a full energy booster. And all the machine, it's based on what we call this multi-bend achromat. I'm going to explain a little bit what this is. And we have an interesting characteristic is all these magnets. So if you see here the logo, it's a Brazilian company that produces motors and generators that actually manufacture all the magnets for this machine. So they went slightly off from their comfort zone, and building is a large company. It's the third largest company in the world that produces motors and generators. And they decided to tackle this challenge with us to build magnet for an accelerator, and we're very successful on that. So I'm going to give you a quick tour inside our storage ring if the video works, but apparently it doesn't. Let's see. Oops. Okay. Yeah. So this is an internal part of the linear accelerator, as I mentioned before, where the electrons are accelerated to 150 mega electron volts. Then they are moved to this booster storage ring, where their energy is ramped up to 3 billion electron volts. And once they reach this energy, they are transferred into the main storage ring. It's where their acceleration produce radiation for the experiments that we will show in the next slides. So they basically trafficate through these ultra-vacuum pipes in bunches like the ones I described, and their trajectories are bent by these magnets that were produced, and they generate light to all these beamlines. Here we show only this longest beamline, but we actually can have 40 beamlines in this entire storage ring. So now the radiation is splitted from the storage ring, and we will move outside the storage ring for our visit. But before we do that, let me quickly give you an idea of what a 4th generation storage ring is in very loose terms. But essentially, if we measure the size of this bunch of electron beams by the geometric mean of 2 main parameters, the emittance and the beta function. So, and the idea is that the smallest you can squeeze this number, the smallest the beam is, the more coherent is, and the higher is the coherent fraction, and the more resolution you have in your experiments. Now, this technology of the synchrotron radiation and the band achromats has been evolving, and we can say that the order of magnitude on the 2nd generations, like the old synchrotron we had here, this dimension was of the order of, let's say, a millimeter. As the 3rd generations moved, 1 order of magnitude was decreased to 100 microns. And now with the multi-band achromat technology that we've been using in MAX4 and ESRF EBS, which is the new upgrade of ESRF in operation. So these new multi-band achromat synchrotrons, they are all based on this 4th generation technology, and the transverse size of this beam is of the order of 10 microns. Now, what we gain a lot from this is what we call the coherent fraction of radiation. This opens up opportunities to get more information. Formerly, the experiments were done using mostly the intensity of the beam and how it interacts with matter. Now, when you use the phase coherence, it's a revolution, because it's basically like what the revolution that we had in telecommunications, where before 2000s, we used to use only the intensity polarization of the beams moving through the optical fiber networks of communication. Now, since the 2000s, we realized that coherently, the world realized that using the coherence properties of the light within the optical fibers, it improved a lot the information you could send to the systems, and that made a revolution. So we expect the same kind of a revolution will be done for synchrotrons. Now we can use more information from the beam of radiation from this coherent aperture, and this allows us to do coherent diffraction imaging, photon correlation spectroscopy, nanoprobes, because the smaller is the source, the smaller is the focal point, and the more fine is your probe. Or you can submit matter to extreme conditions and probe its properties of new phase diagrams of matter. I will show some examples of that, but there are several scientific opportunities in this technological revolution of accelerators. These are some of the parameters of the storage ring. You can see the design layout of the magnets, and these two numbers I mentioned, the emittance and the beta function, that gives us this small beam size that we need for coherent applications and for new storage rings. We have this machine has a special characteristic that most of the fourth generation machines that are now operating, there are only 3, of course, but most of the projects that are also oncoming, the low field dipoles that are used for infrared and ultraviolet, they are typically left outside of the project. And these machines are mostly focused on hard X-rays and tender X-rays. But in our project, we decided to keep this scientific program of low field for ultraviolet, infrared radiation, and I'll show some examples of things that we can do with that. So that of course involved a lot of engineering, but it's feasible and it's interesting because you keep the community with more possibilities for science. Now I'll walk you through one of the beamlines. So the beam is coming from the storage ring. This is a beamline typically. It involves hutches, and then the radiation is conditioned in some of these hutches, and samples are brought to the other ones. This is our longest beamline. It's so-called Carnauba beamline. So it's 150 meters long. This beamline is dedicated to a nanoprobe. So we use this large distance to demagnify the micron size beam to nanometer size focal spot, right? Using basically this arm of the magnification. And what you see now is inside, you saw my image there, but it's the inside of the experimental hutch. It's surrounded by detectors, not like one of those big detectors on large collider, like the Large Hadron Collider, but this is our version. We surround with fluorescence, luminescence, optical microscopes, diffraction, coherent diffraction image, everything you can extract from a beamline. And I will show you some of the results that we've been recently getting from this. This is the Carnauba beamline. It's a tender nanoprobe. And this is the overall plan that we have. We are currently working on phase 1 and starting phase 1A and starting phase 1B of beamlines. Imbuya is the infrared beamline, is the first one of this phase to be built. And we are now working on this several beamlines, of course, depending on budget, basically, but we are now steadily growing the number of beamlines that we can offer for the community as soon as we are able to open. This is a timeline of the commissioning phase. We basically, by the end of 2019, we had the first stored beam in the very small current, but we had one of the microtomography beamlines assembled to make the first wide beam images, tomographic images using the Sirius beam. So we had the beam stored and first images almost simultaneously. And that was very exciting because later on, we were able to increase this current and increase the flux. In March, we were halted by the pandemic, so we had to change our way of operation and adapt to the new world reality with a very small number of staff in the campus, just to allow that the others could continue their work from home, even commissioning and operating instruments in commissioning phase. And then we moved on to started the technical commission of several of these beamlines. By January, we had an alignment of the storage ring, and we started to reach the specification parameters for the machine as they were designed. We're currently working with 70 milliamps in decay mode. We still have to ramp up this current to 350 milliamps. And there are several tasks to move on, but this is already enough to do the commissioning experiments. Now, what kind of experiment that we do? The first question that people ask when they're not from this field is how different it is what you do in a synchrotron light source and what they do at the colliders, right? So in colliders, basically, we collide beams. So we like this animation from the Large Hadron Collider. Basically, we look at the product of collision of particles, and we created a model from reality in the world colliders that defines matter in its most intimate quantum fields, that what we call leptons and quarks and the gauge bosons. Now, you may ask why this is important for the experiments that you do in a synchrotron. Well, it's not like this is what we are going to use our model for reality, but we are all human beings living from the same kind of know-how that cultural evolution brought us here. So it's not surprising that even for in different energy scales, like milli-electron volts to kilo-electron volts, we still try to look at reality the same way. Looking at particles that propagate, they're not exactly like electrons, they are dressed particles like the ones that we see in the reality of these experiments, but they can be polarons or quantum excitations of vibrations or quantum excitations of magnetic order or plasmons or even excitations that we didn't even see yet in quantum fields, but we foresee, like Majorana fermions that and there are lots of trades of knowledge from different areas. Now, we have instruments that probe this. I mentioned one of them is the RIX instrument. This is a result from literature, but that exemplifies exactly what can be done in this kind of machine. This is a resonant inelastic X-ray scattering, where spin, orbital, and charge characteristics of the electrons are separated. So these are quasi-particles. These are not real separation of the spin from the orbital, from the charge, but it's how we see reality from these experiments, thanks to the kind of probes that we have in a synchrotron. Now, we also can see different ways that the fermions can propagate by looking at their momentum dispersion from synchrotrons, and even probe different states of matter by and to reach this kind of excitations by pressurizing the matter in a tiny cells that can reach pressures that are much higher than the ones you find in the interior of the Earth. Now, this is challenging, but you need small beams that can probe inside these sample stages of high pressure, high temperature, high magnetic fields. This is already a commissioning result that we see from the EMMA beamline on Sirius. It's looking at a phase transition from this material. It's one of these candidates for topological materials, but you can see how different phases can be reached by pressurizing the material and looking under the scope of X-ray diffraction. Now, condensed matter, it's a big field, but we have it covered by different techniques. I just mentioned this extreme condition beamline, EMMA beamline. We have also a lab for extreme conditions to prepare samples that go to these beamlines. There's a beamline construction for probing the magnetic and spatial and energy result magnetic structure, the electronic band structure of quantum materials using angular result photoemission, or even resonant inelastic X-ray scattering, and in situ growth labs to build the materials that you will see in these conditions. So now we have these beamlines and experimental labs in commissioning, and the other ones are being constructed. I'm giving you just a flavor of what this extreme condition beamline is. This is an image from yesterday. Scientists were preparing some of the samples to probe. So what you see here is a detector, magnetic field coil, cryostat, the high pressure cell. So all this intricate system to probe matter under extreme conditions. What kind of matter? Any kind of material that you would like to observe it under different conditions that you find typically in the environment. Now, going from materials to the living matter, then we have different questions and different models of reality. Obviously, the same way that we don't think in terms of quarks to see how electrons propagate in a solid, we cannot think about electrons or even just atoms when we try to see the reality of life. We have to start from different building blocks, so-called proteins and biopolymers. So this is the kind of thing that you also have the ability to probe in synchrotrons, is the structural biology, and to measure cells in their whole structure, and then later on use computing models to build like this one published in this very interesting book by David Goodsell, Machinery of Life, where he illustrates the science together with art of what our knowledge of the basic building blocks of life is. Now, Sirius started using, but the first beamline we started operating was a line for protein structural crystallography in the task of fighting COVID. And this was the first structure that was unveiled on the Sirius facility. It was a structure from a protein of the SARS-CoV-2 virus. Later on, we had the users coming to the lab and testing their targets on this virus protein. All those first projects were dedicated to the research on COVID. And also we had the first publication coming from exactly the same problem, where they observed snapshots of the maturation of a protease of the virus. So it's a very interesting international task, and we had the Brazilian scientists contributing with knowledge for this fight. Now, going into this level of imaging cells and larger objects, this is the Katerite Beamline, which is also in commissioning. It's basically a beamline of a small coherent angle, small scattering with a coherent beam. So what you see here is a large area detector that was developed within the project with a Brazilian company. And what you see here is the sample and the beam, and the coherent diffraction patterns that you detect in the detector are transformed into 3D images. So let me show you an example where we first had in the microtomography beamline. This is what I told you. It's an ongoing research project from the LN-Bio, one of the labs of our center, on ultrastructure of cardiac tissue and cells, how they organize and how this is connected with cardiac regeneration, myocyte regeneration. So what you see here is a large collaboration in between what we can get from Sirius imaging processing. NVIDIA has been collaborating with us a lot to use their most advanced tools for GPUs. And this is now a result from taking one isolated cardiomyocyte cell and observing it through these coherent diffraction imaging. This is still ongoing. We are in the process of commissioning, but what we see already is that the internal structure that we can get from this cardiomyocyte can teach us a lot, not only from the cell, but also from the difficulties of doing coherent diffraction imaging. So this is it's very interesting that it's a collaborative endeavor that we have to feed back into the storage ring, into the science of a cardiac disease, into the beamline, into the technical aspect and the imaging process, all contributing to, at the first point, commissioning these beamlines. Science with this kind of system is going to be done soon. And we see, for instance, another aspect of the same project. So they go from the organ all the way to molecule. So this is a protein directly connected to cardiomyocyte regeneration. And what they see here is an inhibitor coupled with a molecule. This is a data taken also in the Manacá beamline of Sirius. As soon as we opened for the COVID research, later on we started opening for other research projects. This is one of the structures that was published in the PDB, the protein database, of target and protein being measured in the beamline. Now, The soft matter in biological matter area is covered by different beamlines. Katerite, I just showed you. There is a small angle scattering beamline, infrared, circular dichroism, so infrared and ultraviolet, and protein crystallography. So all the suite for soft and biological matter together, we hope that will bring knowledge possibilities for understanding life and bringing ideas on how to cure some diseases. Now, moving to the third and last topic of the scientific programs that we are developing, the heterogeneous in hierarchical matter. It's typically it's I showed examples of very homogeneous matter, quantum materials. When we build life, we rely on basically molecules and the entropic and soft interactions in between them. And now when we mix inorganic and organic matter, we can form the several heterogeneous and hierarchical structures like soil. And we do have this lower scale, lower resolution or micro nano computer tomography beamline that I showed you many examples. The Carnauba beamline basically covers this range of 100 nanometers to 1 nanometer, the diffraction and coherent diffraction imaging. And the beamlines for looking at atomic structure of partially ordered materials or even crystallographic structure of materials like different mineralogy in soil, or even looking at local chemistry using X-ray spectroscopy. So again, this forms this heterogeneous hierarchical matter program, scientific program for the Sirius. And I'll give you one example is, so I showed you the standard model of particle physics, as we call. Then we move to a different level of how we see electrons propagating in materials in our standard model of quasi-particles. And then we move to a zoom out of how molecules form our standard model kind of life. And now when we move to soil structure, we have a mixture of inorganic and organic compounds, which forms this ecosystem where all life on Earth relies on. And then we have different length scales and types of matter that we have to probe with all this kind of tools that I just described. This is again Carnauba beamline. You see, this is where the sample goes. The detectors, the fluorescence detectors, they basically take the sign that corresponds to certain concentration of elements. So you can combine the image with the scanning probe of where these chemical elements are in your sample to form a complete view of the soil. So let me give you an example of first starting from microtomography, again from the Mogno beamline. So you see the interface between grains and fluids and the plant and the plant root. And now when this interface in between the plant and the soil is what we call the rhizosphere, it is where most of the biological processes relevant to life and must happen in this exchange between the inanimate and inanimate matter. Now, this is one of the data of Sirius. This is again another data taken on Carnauba. So there's basically a root that we use to do microfluorescence measurements. So you can basically probe the concentration and correlation between different chemical elements. Again, all this data that I'm showing you, these are commissioning data, but we are already bringing sample from users to help us with the commissioning. This helps a lot to tune up instruments, sample stages, and resolve problems. But you can get a flavor of what kind of science you can do in the future. Now, again, nanotomography for this microparticles where you find in soil using Katerite Beamline can be done, or infrared to do images of microorganisms and how they interact with the chemical aspects of the soil. Now, bringing all this together is hopeful that we can get this heterogeneous picture of the ecosystem and how the interactions between microorganisms, plant and soil happen, and how do we solve problems like phosphate and like phosphate fixation in tropical soils. This is a huge problem and is one of the scientific programs that we are dedicating a lot to understand how do we extract phosphor from soil and how do we do a better fertilization, because phosphor is one of the nutrients that we need in the soil, and it is a mineral resource that is going to end at some point. So now, still in this idea of using, not only trying to understand the soil, but also using the know-how of evolution and how it created organisms, that microorganisms that live in the soil and can destroy the biomass. So we can use this know-how, and this is what LNBR is doing, how to design enzymes based on what we find in the microbiome of the soil, so that we can also break biomass and produce goods and chemicals for the industry without the need of fossil fuels. So again, this is a protein structure done in the Manaka beamline. Now, we are developing several stages for samples that you can use in different samples, like this rhizome microcosm or microfluidics, electrochemistry. These will all be available for users to do these different structures of health sciences and environmental and energy and functional materials. Now, to summarize, we've seen some of the beamlines that can do different, that they can cover multiple spatial information, and from structural to electronic information, and leaving to functional to quantum matter. Now, we showed some examples of how diffraction it can be used in different beamlines, from unveiling the structure of proteins all the way to looking at materials under extreme conditions. And X-ray spectroscopy, how can we use later on to probe these quasi-particles and how they propagate in solids, all the way to how we establish chemical bonds in soils, to how we probe secondary structure of proteins with UV information. Now, all together, these are the beamlines of Sirius, and that we hope will do all these scientific cases that I hope to have convinced you of their importance and how we are moving along in this trajectory. Now, we had to develop most of the instruments we've been using. Just a quick few examples of things we develop with local and international companies. This is our basic double crystal monochromator. Is a core of the beamline, is the instrument that requires a very large stability. So we need to keep this optical system stable down to a millionth of a degree. And this required technologies that we didn't have at the time. So we partnered with this Dutch company that was specialized in mechatronics innovation in other areas. And we remodeled the concepts of optomechanics for monochromators for these new systems of Sirius. We have already probed the systems and we've been working with them. This is a nice spectrum. You can see X-ray spectrum using this new high dynamics monochromators, even doing fast scans. And you can see it's like a textbook example that has been done in EMA beamline using this kind of monochromator. Obviously, not all are flowers, and we had been going through several different problems, but as we know, we remove one problem to get the next one, and we understand better the systems. They are not perfect. These are all designed for experimental science, and part of the science is finding out their limitation. Right? It's the most important part. So we stumble upon many of these limitations and we solve them. Now, this is an infrastructure of labs. We plan to cover also the initial steps of an experiment, not only providing the beamlines, but also infrastructure for, like this lab for thin film grow, or this lab for pre-characterization or assembling samples into gaskets for a diamond level cells, or even pre-characterizing the samples that are later on going to the beamlines, either in very high temperature or like this cryostat being developed to reach very low temperatures in the beamline. This is not commercial, it's specially developed for the beamlines on Sirius. Last but not least, computing infrastructure is fundamental law. Like you prepare your samples, you do the experiment, and you are going to spend most of your time analyzing data. So we are providing this computing infrastructure for users. The volume of data is enormous. We don't expect that users will simply download their data, but they will use our storage data center and cluster imaging clusters to process their data while they are doing the experiment and once they leave our facility. We had most of our developments done with local industries, and most of our purchases actually done in Brazil. So it was a very important mechanism of equality, is a mechanism of spreading knowledge to industries and to people who would never otherwise work with such advanced technology. So companies that moved from their, let's call it comfort zone of their own technological niche, that moved into building instruments for a fourth generation synchronous storage ring, they acquired knowledge, they diffused this knowledge to many of the, and created many employment. And I think that this is one of the most important aspects of any one of these large scientific endeavors, is how can you diffuse knowledge through different areas and different parts of the population. My closing remarks. So we had to adapt to the pandemics, but thanks to this very collaborative team, we are moving on, not maybe at the speed that we wished, but given the circumstances, I think it's been great. Machine and beamline commissioning are happening simultaneously. It's challenging, but as I said, it offers opportunities for integration. We are close to the nominal horizontal emittance and to some of these key parameters of the machine. We have still to improve on stability, and for that we are building our fast orbit feedback system, and we plan to, by the end of this year, start to have the top-up mode of 100 milliamps. Increasing the current will require the installation of the superconducting cavity, which is already built, but will be installed in the years to come. We had several in-house developments and operation that are operational in beamlines, and the experimental facilities for lab sample preparation and high performance computing. And we are already doing the first measurements with user samples. Some users can access the campus, especially depending where they're coming from. And we have 5 beamlines currently doing experiments, and 2 more will come in the next months. So we plan to hopefully begin 2022 with 7 beamlines doing experiments. To finish, I just quote Thomas Piketty on his view of the most inclusive way or convergence factor in the world as being the knowledge diffusion and internationalization of that. So with that, I thank you all for listening, and I'm open to questions.
Excellent. Thank you very much for this extremely comprehensive presentation, and very exciting as well to see everything that can be done in the southern hemisphere. So we have few questions, for instance, in the chat and the question and answer. So we will start reading them, and by that time as well, feel free to enter those questions or raise your hand, and then we can as well give you the voice and ask live your question. So I would start maybe by the first question. So from Fabien Odobde. So he was mentioning or asking how to be able to join the project. So if you're a student, depending on your background, are there any constraints so that they can join the project, and potentially describe the scholarship and the different aspects as well?
Sure, there are several ways that we can join the project depending on the phase of your career. We have opening positions all the way from being a student developing your graduate studies, to being internship, doing summer schools. We provide training schools for synchrotron. We have a Brazilian school for synchrotron radiation every year. We also provide training for teachers on high schools that can also participate and learn what is being done, so that they can also diffuse this knowledge for the high schools. And we have opening positions for engineers, for technicians, for scientists. I can try to put the link. I'll try to send the link as we go. But yes, you can join the project several ways. Collaborating, if you are in a university and you wish to use one of this beamline as a user, or even to develop new instruments, and also participating, working with one of these industries. They also have positions available for engineers, technicians, scientists in the most diverse areas. Here we have employees from scientists from background in chemistry to biology to agronomy, from all physics, all areas. So I hope I answered the question. Yeah.
Yeah, it's really multi-physics as well needed to operate overall. So, and then we will also share the link that you will send potentially and your email as well, where we can as well address for the command. So there is as well a question from Daniel speaking about the procedure. So applying for the thin film fabrication at your facility. Can you comment a little bit on that?
Yes. Typically, this is going to be, we designed this facility to be connected with the synchrotron. So initially, it was connected to the beamline in our former synchrotron. We decided to improve, enlarge, and move it outside of the synchrotron because we figured that there is much more power in preparing samples while the other users are using the beamline. Applying for this typically has to be connected with a synchrotron measurement. So this facility is not just a thin film grow facility. It's a facility connected with the synchrotron beamlines. So we are currently not open for proposals yet. We are waiting for authorization from our contractor to open this. We are technically receiving users in this user commissioning mode. But stay tuned. As soon as we get this authorization, we'll open the facility, and like this thin film lab will come along with the beamlines that will be able to use it.
Very good. So we have the next question from Samela Sal. So whether she will speak up, I can give you the voice, or I can read it. So Samela, or maybe we can just say, so she's interested and she's working, I know now as well, on the Mongo beamline, so to study the biological sample, so just as the tumor tissue, and learn more about its chemistry, chemical element distribution. So can you say more or less when this beamline would be ready to accept proposal? And or I could add as well, how all those different topics could potentially be connected to other beamline and to other so synchrotron around the planet. Is there any synergies as well where she could also be involved in potentially for her study?
Yeah, that's a very interesting question. The Mogno beamline, we had we started this beamline. The images I showed was now going into details. It was in a previous assembly of the beamline. We were still waiting for one of the mirrors that composed this beamline. And we were working basically with the pure pink beam from the storage ring. Now we started assembling the beamline for using this new mirror, which will increase the resolution and reduce the sample damage, which is extremely essential for biological samples. But as many places in the world, we are suffering from the external providers of instruments, and we're facing some delays. I believe right now we have this mirror being shipped, and we hope to start reopening the beamline at the beginning of next year. Now, regarding a question of mapping chemicals using X-ray tomography, perhaps is not the best way of doing it. I don't know what kind of chemicals you like, because X-ray tomography will give you a color map, let's say, of attenuation of electronic density. You can find distribution of some chemicals. It's not exactly the best technique. Probably a scanning probe technique is more suitable, or either in the infrared range or in the X-ray range, depending on what kind of elements, and if our molecules, if our targets. So I'd like to know more, but yes, there's a complete suite of beamlines that you can use either here or other synchrotrons as well. But regarding Mogno beamline, you should expect more for the beginning of next year, the reopening of this beamline. Sorry, Christine, I think you're muted.
Yeah, sorry, indeed. So, and then we have another technical question as well in the question and answer section. So about, so from a Queen Key, who is asking the main obstacle to increase the beam current from now the 70 milliamps at the moment to the design value. Excellent.
Well, thanks. The questions are really great, actually. So we are currently, it's a kind of a technical aspect, but to maintain the current in the level that it is, we need something called the RF cavity. Now, we are currently using an RF cavity that is based on a normal metal, copper. Now, we could use more cavities like that to increase the current, but our decision was to use a superconducting cavity. So it's kind of, we have to replace the batteries that are moving the electrons. Now, this kind of battery that moves the electrons is based on a superconductor. And so now the cavity is ready. We have to install it. And we are installing the cryogenic plant that will cool this, because superconductors have to work at cryogenic temperatures. So the main obstacle right now first is to install the systems. And this might take still a year or more to finish the installation of these cavities in the machine. Second, there are other subsystems that we still have to commission in the machine so that we can increase the current. And we will have also to install some devices that kind of stretch the electron beam so that we don't have too much interaction between electrons and we spoil all this good emittance. So there are some technical aspects of what has to be done. It's all on track, let's say. But my feeling is that right now, that's not the major, let's say, the major limitation of the experiments. That's what we figured out, that there's a lot to learn yet with even at 70 milliamps. And I think by the time I hope that this will be the limitation of the experiments very soon, and we will desperately need more current to run faster experiments. But yes, these are the main things ahead of us, replacing the cavity.
Very good. And with cryogenics, which is a big deal, definitively, to make it effective.
Definitely, it's all new for us.
No, on that. So, and then we have maybe a further questions as well from Samela. So I gave you the possibility to speak, Samela. Do you want to ask it live?
Yeah, I can. There's just some noise behind here. But can you hear me fine?
I'm sorry, Christina, I couldn't understand. I don't know if you can translate.
It was not maybe so clear. So Samela, do you want that? I will read it if you want. So in the chat box, so indeed, so she asked, so do you know, so what different possibility of photon accelerator would be compared to an electron accelerator? So is the electron accelerator better and has more advantage? Can proton be used to study biological sample as well?
Okay.
So was it clear enough?
I think so. If I understood correctly, please correct me if I'm wrong, but if I understood, the question is, would it be better to use accelerate protons to do the experiments or electrons? It would be, in fact, the amount of radiation that you get from these charged particles depends a lot on the mass of these particles. The lighter the particle is, the more radiation it emits. So it wouldn't be practical to use protons to produce synchrotron radiation. They are too heavy. So not for this kind of experiment. So if there was something lighter than electrons, probably we would be using it, but unfortunately we don't have it. So that's as good as it gets. So yeah.
Indeed, from the design point of view, synchrotron is coming from the electron, we agree. But then maybe what she could look at is rather with the proton that accelerate and with spallation, then you have neutron beamline and then the same scattering. So there maybe the resolution could be as well different and complementary. So electron and proton for accelerator science could be complementary for that, for the scattering and the photon. So that's a good question still.
That's
so
an excellent question.
Proton accelerator are important. I stand for that. And then we have another. Yeah, please go ahead, Alan.
I'll just point out that at Los Alamos we have a proton beamline that goes directly into materials, not as a spallation source. So we use the protons for some imaging aspects, but it would not really be appropriate for biology. We use it for metals and and very dynamic experiments.
Oh,
But the advantage is that you can actually focus, you can do imaging with protons, unlike neutrons, of course. But I have another question, Christine.
Yes, please.
Or for Harry. I'm impressed with the, first of all, with your standard model paradigm for explaining both materials, quasi-particles, and even biology. That's fun. But there's some really interesting aspects to your extreme conditions beamline, Emma. Can you, or would you be willing to run actinide materials?
Yes, that's exactly within our timeline we actually are going to install a lab for actinide materials next to the beamline. And this is within the next phase. Emma beamline has 2 experimental stations. This is the first one. And the second one will be dedicated to a nano-focus beam. It's in tandem with the first one. Next to the beamline, we have labs, as I think I don't know if we were clear from what I showed, but one of these labs is going to be an actinide lab to run this kind of scientific case. You're absolutely right, Alan. It's a tremendous scientific opportunity that we're going to explore.
Good to hear. Thank you.
Very good. So I think it's good to see that the border or the boundary as well of science are growing. Now, indeed, it could be even with the next question as well. So by Danielle. So it's also another technical question. So so are we able to perform the wings for the X-ray scattering for the morphology characterization of the 2 or 3 dissimilar electron affinity polymers? So
I'm sorry, I had a problem with the audio. It was chirped. Could you please repeat?
This is the asking question about for the G-wax and then the G-SAS. So it means that for the small angle X-ray scattering or for the wide angle X-ray scattering, is it some kind of possibility for the morphology characterization of the 2 or 3 dissimilar electron affinity polymers? So it's very, very advanced and specific, but is it clear enough, or as a question we could
yes, if I understand is how can we differentiate, have contrast enough, if we would have contrast in small angle or wide angle X-ray scattering for these different polymers. I believe you can. There are probably more, again, other opportunities. Probably soft X-ray microscopy is one of these opportunities. You can get very good differentiation between different polymeric change by doing image tuned up to specific energy and energies near the carbon absorption edge. This is either by what we call scanning transmission X-ray microscopy or even photoelectron emission microscopy, or yet differentiating polymers using nano-infrared as the beamline I mentioned. You certainly have different signature fingerprints of these different polymers within the infrared range of the spectrum. And using a nano-infrared gives you also this differentiation with, let's say, our best resolution now is of the order of 100 nanometers, if this is the kind of range you need to differentiate localization. But yes, indeed, small angle scattering can give you morphology, and wide angle scattering certainly can give you some aspects of the crystalline or semi-crystalline properties of these polymers if they have enough, let's say, differentiation in this range. Yes, it can be also. Typically, a beamline experiment is not a panacea. You don't solve your problem using one single beamline. And I think that the analogy I tried to make is it's somewhat of how you run high energy experiments and how you run typical experiments is to give an idea also that all these questions about can I do this, can I do that, they come before making the synchrotrons are kind of hypothesis testers, like any kind of accelerator. So you have to come with a hypothesis, microscopic hypothesis of how things are interconnected, and how would you, looking at an aspect, answer this question, right? So if this happens in the soil, and this is my model, microscopic model of the soil, so this must happen that, you need to find the signature in X-ray spectroscopy. Or if these polymers have this affinity and characteristic in mechanical, and this is my microscopic model, how can I probe this? Design an experiment. So you will not find a full report of what you're intending in a synchrotron. And typically these are, I have to be very honest, these are tough experiments, and you have to bring good hypotheses of what you need to do. Once you can do that, you have to combine different techniques to answer your questions. You will not find all the answers in a single experiment or single techniques. Sometimes you may, like protein crystallography, it's a very standard experiment. But for most problems in material science, the true art is in combining, all that was done to build up the standard model of particle physics. You have clues from different sides, and you create the whole picture of your system. That needs explanatory power most of all. And this is what you can get from these models.
Excellent. So I think it was a very comprehensible answer, isn't it, Daniel? I guess now. So then maybe one of the question as well that you raised was how important as well the synergy with the locals as well have been in the evolution and the construction as well of the Sirius. So this is one aspect that could be interesting to understand for the next, not generation, but the next light source as well that will be implemented in the world. So which type of advice, or what was the pro and the cons to have the Brazilian community, so from the politicians all the way to the industrial, being able to set up as well and give some support for the Sirius to be, and what was the life cycle or the time frame from the beginning of the project till the end, while you already had one laboratory? So I think it's important to take this.
Yes, excellent question and excellent points. So indeed, it was absolutely crucial that this first synchrotron was built in Brazil with Brazilian technology, and all this path was followed by the pioneers of synchrotron radiation in the country. So there was no community on synchrotron radiation, and could barely count the number of people that were using X-rays back in 1987 when this project for the first synchrotron started. So there was no community, there was no technology, there was no user base, there was no know-how. So we relied a lot on the community, and we had groups of scientists going to Stanford and to learn about accelerator physics. We had groups of scientists learning X-ray diffraction across the world, postdocs in other institutions. And we had pioneers like Professor Ricardo Rodrigues, who unfortunately left us a couple of years ago, and who basically laid off the path for all this cultural evolution that we had along the years. So this was crucial for the first project. Was I think the major narrative for the first project is that we can build such an infrastructure in the country, and we can create this community. So this I think was accomplished, and it was important to convince everyone that this investment was well made. So you always have to prove that your point that the investment done fulfilled your objectives. And the main objective of this point, the first project from 87 to 97 was built, the first synchrotron, and that operated until 2019. So the main objective was to create the community and the technology. Now, thanks to that, we were able to, we had all the know-how from vacuum components, power supplies, beam diagnostic detectors, optics, everything was installed in-house. So that allowed us to think further. Of course, now comes the best advice. I think that when you always need a good narrative of your project, everyone's buying into it. We are humans, we collaborate around ideas, and it's sometimes even hard to express how simple this is and how important this is. Now, the second project, the major narrative was that, okay, we had built a community, we had built a synchrotron. Now we had to do something that is highly competitive internationally. It's not only a new synchrotron because that doesn't buy anymore, right? Second point that was absolutely crucial, we need to increase the user base nationally and internationally and give the opportunity to interaction. This synchrotron is kind of a gateway of international collaborations. You have people coming from other countries. This is also increases the knowledge base in the country and abroad. And third was what you mentioned was when you develop instruments like that, right, in a country that is in development, you have the scientists, they have access to technologies that don't necessarily permeate local industries. They might be working in things that are quite advanced, but they don't have the same outreach that we can have interacting with international laboratories. So we're kind of an entrance point, gateway for the knowledge as well. So when we say to the politicians that we are not going to do it ourselves, we learn how to do it ourselves. We know how to do magnets. We know how to do vacuum pipes. We know how to do detectors, but we're not going to do it ourselves because we are going into much larger enterprise and we will include them in the equation. We will teach them how to do for us, right? And this creates a knowledge diffusion, we impressively way of equal distribution of goods because you invest in the country, but the end result is that there's a large population that will be trained in things that they wouldn't otherwise if it wasn't for this large scientific enterprise. So you are distributing, you're funding knowledge through big projects like that. And that I think was one of the things that by the most, when you show detectors that are built in town, that are being maintained, when you show hutches that local companies learn how to do, and they are selling for us and will be selling for other synchrotrons, I think that I heard from many different politicians that that pays off already, the project. When you show something like this, you're paying off the project. I know many other developed countries understood that quite well already, that doing large enterprises like that it's a very inclusive and it's increases the knowledge offset of the entire country. We're learning that, and I think that's the most important message for developing countries and for new synchrotrons, that you have to, this component has to be in our equation all the time, that you're not just building a nice toy for scientists. Of course we're also doing that. We're scientists, we want to use this nice gadgets and find and answer questions about nature and create models, but that's not the only purpose of it. I think that you have to include in the equation all these other purposes.
Yeah, that's really important to see that, and for the operation as well, for the long-lasting possibility as well to operate those light source. And for the case, for instance, of Sesame now, so if we come to the possibility, exactly, I see a hand raised by Andrea, because I would like to have as well now the understanding in terms of observer, how this helper country as well can provide information. So Andrea, can you maybe find ways to
Yes, so I was wondering, okay, first of all, I answer your question. So what is the role of the observers in the development of Sesame? That has been absolutely crucial. You see that if you look at the numbers, so 8 against 18 observers, it might appear peculiar, but might appear strange that there are more observers than members, but observers for Sesame are the countries which are helping us in developing Sesame. So it's the countries who are the most willing to share their knowledge, their training, where our scientists, our technicians went during the early ages and still go to get informations, and users come from there, and equipment comes from these countries. So they have been extremely important for that. They observe and they help us. I want to add one more question to the magnificent picture that Harry Waits let us learn about the development and the history behind this fantastic enterprise of Sirius. And that is the role, if you could maybe tell us a bit more about the role of the science center you are embedded in. So there is, does it came together after, before it developed? I think that at certain point the things develop together, I guess, because the sheer size of Sirius with respect to the entire campus. But did it come before or after the
Andrea, thank you very much for raising this point. I think it's absolutely crucial, and I thank you for raising that, because it's this center was created around the synchrotrons first. I'll give you a quick history, perhaps not so accurate, but once the synchrotron was installed, it was clear, of course, that structural biology was needed. It was one of the most important tools, but to be able to do structural biology, you need to prepare crystals, you need purification, you need cloning, you need all the infrastructure, which is not necessarily installed in the entire country. So there was the creation of a center inside the campus to foster the scientific enterprise of preparing crystals to reach the synchro beamline. And with that, also electron microscopy was seen as a fundamental complementary technique. So another infrastructure was created, and so on and so forth. At some point, the bioethanol was on the top of the list of fuel and development in the country in energy. So all these labs were entering this campus and joining also this synchrotron science enterprise in different ways. And nowadays, you can see from the examples I showed you that it is absolutely crucial that they are doing the experiments with us, because you know that when you do an experiment, when a user comes to do an experiment, if you don't know exactly the protocols for sample preparation, you haven't done this experiment before, it takes some time until you reach, the great experiment they will do. Now, having these labs with their different capabilities in the campus and being across the street to be able to bring their samples and to, think with us, okay, this is damaging this, we have to go back, we need to do staining, you need to cut this way. It's something that is very hard to do with a user that will stay here for a couple of days. Now, if you are prepared, this kind of science you do with these labs feeds back into the development of the instruments you're doing for the community. So it's a kind of self-reinforcement mechanism. You do science in the synchrotron and in these labs using the synchrotron, but at the same time, you give back to the community because you understand several of the protocols that are later on used by the users on sample preparation, like in nanotechnology, like stream conditions. So everything that is being used and being done in the science is highly crucial if you want to bring to the community something that is already more, let's say, prepared for extracting results. It's absolutely crucial. This has been, I think, one of the key success points of this, especially the scientific enterprise that we are entering now by starting the commissioning of Sirius. It's an excellent point. Thank you for raising that.
Very good.
And Harry, do you have a guest house
yes,
for all of these users?
Yes, we do. It's a small guest house. We need to improve on that one because it was prepared for the other synchrotron, and it's on the list of things to be done. Yes, we do have a guest house. We have thousands of users that used to come on the other synchrotron. We were having a user base of thousands of users, but we need much more guest house space room.
Very good. And now I also allowed, so we have Carlo Enrique, so de Brito Cruz, who is asking you a question, but from what I understand, he's also connected as well.
Oh, yeah.
Study. So maybe he could ask the question live to make it a bit more vibrant.
Sure. Thank you, Christine. I'm happy to do so. Hello, Alan. How are you?
Hi,
Hello,
Brito.
Harry.
Nice to see you. Good to see you.
To you. It's been some time.
Yeah, nice to see you.
Very good. It was a great talk. I was going to ask you to comment a little bit on how you worked with industry in Brazil to develop parts and pieces and services for the for the machine. We had that nice program with FAPESP, with the small companies, and you had several other interactions with large companies, because a machine of this type lends itself to several opportunities to develop local technology.
Absolutely. Thanks for the question, Brito. So yes, I think that I mentioned before, one of the crucial points of the project is it was not that when you budgetize your project and you interact with funding agencies like FAPESP was interacting with us in this aspect, you don't only include in your budget building beamlines, building synchro, but you have also to put in equation the funding that is required to prototyping devices, developing devices, and that the local industries will need, because you don't expect that they will use their own resources to do these internal developments. So we worked in several different ways. You mentioned one. FAPESP opened a program where we established challenges for these local companies in the state of São Paulo, and they built some of these prototypes that were later on either used or not, but there was a challenge. It's like and they did research and development on these devices, and also in the budget of construction for Sirius, we also had it included in the budget, this development prototyping with industries. So this was crucial, because if we only had the budget to purchase, you don't give opportunities to local industry to develop. You basically are putting a large threshold of not only technical development, but price as well. So you need some time to develop it. We started that right in the beginning of the project by 2012 is when we started already collaborating with them so that they would be ready at this point. It takes several years. We had several attempts. Some of them were highly successful. Some of them we didn't succeed, but all in all, I think the success rate is probably unmatched by any other synchrotron as far as I know. It's a high success rate of companies that are now succeeding in providing equipment, thanks to this kind of funding that you mentioned, and the funding of the Sirius project itself from the Ministry of Science and Technology of the federal government.
Thank you, Harry.
Thank you.
Yeah, that's an excellent and important point, definitively.
Absolutely.
Then as well, we have then one more question that just popped up. So from Danielle, so you have talked about the need to increasing the number of users based on international opportunities, I guess. So any offer of back type proposal after acceptance of project or an hybrid thereof?
Sorry, I couldn't understand, Christine. Could you please repeat?
Yeah, I'm just reading, so I'm not sure. Maybe Daniel, voilà, he sent as well a link as well. So what we could do is based on a citation. So I guess that what he is asking about the increasing the number of user base of international capacity, I would guess, and if there are any offer for this type of proposal, so after the acceptance of a project. So maybe related to the first question and the answer that you gave.
Yes, we actually, as an open facility, we expect that, and typically this was in the other synchrotron, we didn't select proposals based on nationality. We have basically the proposal calls are open to everyone, and we don't make any distinction if it's coming from Brazil, from Latin America. The only difference that we make from Latin American countries is that we have a funding program for trips for researchers coming from Latin American countries. So we actually can help with the travel costs. If you're not from a Latin American country, then this program it doesn't work. But nevertheless, the competition is open for everyone. So we just have we have committees that evaluate proposals periodically. That was in the former synchrotron. Now we will still reestablish these committees for the new synchrotron, but I believe it will work exactly the same. Maybe we will increase the number of calls per year, But otherwise, I think it's going to be the same as it works in most synchrotrons in the world.
Very good. And I think indeed he was speaking about the people, but as well about the sample for remote measurement. So all this capacity as well that you reflected for online or offline, so measurement.
That is a very excellent, very nice point, in fact. There is a big tendency now of synchrotrons operating remotely. And I do think, obviously, the pandemic taught us a lot of what can be done remotely, what cannot. Well, thanks to the kind of technology that we have, we are now being able to speak, all of us, and have this discussion. Experiments can be done, and I would call them measurements. Let's separate these two kinds, right? So you have measurements. Let's take a batch of protein crystals where you can put them all in a viewer, and you remotely operate the experiment, and you do all your crystals or Osmonga scattering or powder diffraction. So this kind of measurements, they work quite fine remotely, and we do hope to very soon be able to provide them as remote operation. Now, there are experiments where you need to prepare a high pressurized sample, or you need to interact with gases for in situ catalysis, or you need to do stretching of samples. This kind of experience, I don't expect that they will run remotely. They are complex, and they need full attention of scientists, not only for the experiment, but also to sometimes you need to have ideas looking at your experiments. And this kind of human interaction next to the experimental station is absolutely crucial for the users and for the internal staff, because there's a lot of exchange during these experiments that you learn a lot how to better do an experiment. It's not a simple microscope that you simply put things and you get the results out. So I think there's going to be a lot of remote operation, but it will not substitute. A synchrotron will not fully operate remotely. I think there's a fraction of can be done, but personally, I don't expect that this is going to be the case. I think that there's still, we need people interacting with people in the experimental hall. I think this is crucial.
But maybe, as he mentioned as well, this hybrid capacity, because you can have experts locally who could operate if it's for extreme sample environment, but the sample itself could be as well with the data processing and with this high power computing as well capacity being analyzed elsewhere in remote.
Definitely. Yeah, this happens a lot. And to be honest, right now, that's how we were doing. Even the people that bring samples, we are allowing one person only coming to the campus for this user commissioning. The rest of the group is outside working remotely. So yes, I think this hybrid is a good idea. Yeah.
Very good, very good. And then this is interesting because it links us as well to the possibility to close maybe as well the event. So do we have any other question that or people who would like to answer live? And if not, because I see that we have as well our next guest somehow involved in this presentation. So I don't know if he wants to speak, but what I would just point out, so I'll show here, so the next presentation, so that will be also on high, so power computing and capacity for quantum mechanics to show the next limit. So that's a presentation that will take place in Iran. So with Professor Karim Epour, and we will have as well the honor to have an introduction from the president of the Iranian Physical Society. And this will be really interesting as well. So to complement as well our interest in trying to define the new frontier of physics. So I think it's an excellent capacity as well that we try to establish through picking light source as a potential, and then having the possibility to listen to wonderful presentation like the one today of Harry Westfahl. So we really strongly encourage to disseminate also the information. The recording will be available in 2 or 3 days or in less than a week. And then we can so meet every month from now on. And if you have further questions, so you have the different email where you can reach us, and we are more than happy to be able to answer to your question as they come. So on those keynotes, I would like to thank again, so Harry, for his wonderful presentation. And if we have some more comments, please feel free to speak up. Otherwise, we may, because we're right on time now for this given hour, so we will leave you go back to your initial work with this added knowledge that we gain from Sirius, the brightest star and not only a star. So this is a capacity building as well in the southern and in the hemisphere. So
it was very lively. It was a great discussion, I must say. It was very lively and very great. Thank you very much, Christine, for leading us. It was really great. Very nice. So thank you, everyone, for your participation and for this event that was extremely vibrant. So thank you very much, and looking forward to see you next month. Bye. Bye, everyone. Bye-bye, everyone. Thank you.